Today, we're going to look at analog to digital conversion for audio signals. Now, why do we need to do this? Well, if we think about continuous time systems like our ears or our voices, we can represent them as a voltage signal that changes with respect to time in some random fashion. Now, for analog signals, we call these signals continuous time. In other words, we can continually hear changes in sound. And these signals also have infinitely many levels, or infinitely many amplitudes. In other words, I can hear every individual point between as sound as the signal traverses this curve. Now, in a digital domain, we have discrete signals. In other words, we might have to wait for the clock of a microprocessor to do some kind of processing step. So we would hear a signal at this point, and then at this point, and then at this point. So that's a discrete signal. We only get points. We don't have the connection in between the points. And these discrete signals have finite output levels. So we had infinitely many amplitudes between each of these points that we could hear in an analog system, but in a digital system, we have finite amplitudes that we can represent. As a for instance, everybody's familiar with the Nintendo Entertainment System, NES, which was an 8-bit computer. With an 8-bit computer, we can represent 2 to the 8 discrete levels, or 2 to the 8 is equal to 256 discrete levels. So you can imagine that instead of dividing this nice smooth black curve up into infinitely many levels, you could only divide it up into 256 different levels. So, to convert from analog to digital domain, we need to convert from continuous time with infinitely many levels to discrete time with finite levels. We'll look at an example of a 3-bit converter. So a 3-bit converter means that we have bits 2, bit 1, and bit 0. And each of these codes can correspond to some combination of these bits. Well, with these bits, we only have 8 possible combinations. They are the following: 000, 001, 010, 011, 100, 101, 110, and 111. This corresponds to code 0, 1, 2, 3, 4, 5, 6, or 7. So let's look at a continuous time signal and see how we might convert it into a digital signal. Now, one thing to note is that when we're converting from discrete to continuous time, the sampling frequency must be greater than twice the frequency of interest. the maximum frequency of interest. This is so that we can reconstruct that maximum frequency. So for instance, for our audio signals, if our maximum frequency of interest is 20 kilohertz, we would need a sampling frequency that was greater than 40 kilohertz. And in fact, in most of your CDs, the CDs are sampled at about 44 kilohertz. All right, so let's look at a random signal. We're going to divide it into 8 discrete levels. Okay, so we have some signal. And we want to convert it into a digital signal. We need to sample at a regular interval. So let's say we sample at T1, T2, T3, T4, all the way up to Tn. And all we need to know is that the step between T1 and T2 is the same as the step between T2 and T3, and so on and so forth. Now what we do is at T1, our analog to digital converter is going to look to see what the amplitude is at that time, and we can see that the amplitude is somewhere between 2 and 3. So we would output 2, which corresponds to a code of 0, 1, 0. We would go to T2 and see that our output is somewhere between 6 and 7. So 6 is less than VO of T2 is less than 7. So we would output a 6, which corresponds to 1, 1, 0. And we can keep going all the way to Tn, for instance. See that Tn is somewhere between 4 and 5, so 4 is less than VO of T sub n, which is less than 5. And so we'd output a 4, which is a 1, 0, 0. And so on and so forth. So we would keep doing this, sampling every period of the clock, figuring out what the output amplitude should be, and outputting a code corresponding to that output amplitude. Now, of course, we can also do this using a LabVIEW program, which we'll do tomorrow. So we have a signal coming in from the MIDAC. It's being split into stereo channels, and each of those stereo channels goes through a data converter that has a variable number of bits that can be set. And we can look at the signal. So this is the left channel, this is the right channel, and see that after it goes through the system, the analog signal is converted into a sequence of bits. Now, because we can't represent infinitely many bits, we get some noise, and the noise is called quantization noise, and it has to do with the quantization of a signal with infinitely many levels into a finite number of levels. And this noise just sounds like noise that you'd hear on a radio. So we can listen to an example. So you listened as I changed the number of bits from 8 bits down to 1 bit, and you could hear the noise certainly increasing. Although, interestingly, even at 1 bit, we could still make out the music. We'll do some investigations of this tomorrow in class.